Good morning, class. Today we're going over dividing radicals. It's kind of like multiplying the radicals because whatever you can do to one of the radicals, you can do to both as long as it's the same index or root, which is the majority of what we're going to be dealing with today. So I've got the quotient property right here. So it just says when you've got the nth root of A over the nth root of B, it's the same as having the nth root of A over B. Same thing like we had done previously with our product property. So just like this, when you have the nth root of A multiplied by the nth root of B, it's just the same as having the nth root of A times B. So here are just two quick examples, and we're going to go ahead and go over how we can use them in context for our actual problems. So our first one, it actually gives us a cube root, so that means we're going to need 3 of something in order to move it outside of the radical. So let's go ahead and see what we can do here with this. First of all, we know from our property here to the left that we can go ahead and write it the whole thing as a cube root just like this. So I'm going to go ahead and simplify it just here. I've got my cube root over the whole thing, 54x to the 6th power over 2x cubed. So the next step is going to be go ahead and simplifying that. So 54 divided by 2 and x to the 6th power divided by x cubed. Basically, we know that when we're dividing variables with exponents, we're going to subtract the exponents, and of course we know how to divide our integer as well. So we can simplify that one step further down here, the cube root, and it's going to give us 27x cubed, because remember we just did 6 minus 3 as we're dividing our exponents. So this happens to be a perfect cube. We're going to get to the next step where we need to identify perfect square factors when we're doing the square root of something. But as far as this is concerned, 27 is the same as 3 times 3 times 3, just like x cubed is the same as x times x times x. So because we have 3 of something, we can move it outside of the cube root because our index requires 3 specifically. So our final answer right here is just going to be 3x. So that was just a quick example of how we use this property here to go ahead and make what looks like a complicated problem into something a lot easier. So the next one, we're going to basically start off the same way, but then we're going to get to the step where we can identify our perfect square factors. All right, so this one, it just has a square root, but we're going to go ahead and rewrite it into a form that might be a little easier to work with to begin simplifying. So now I've got my 48x to the 8th power, y to the 10th, all over 3x cubed, y to the 12th. So right off the bat, 48 divided by 3 is 16. So now I've got 16 still in the numerator, x to the 8th power divided by x cubed. Well, we've got 5 greater powers of x in the numerator, so that will remain there. Meanwhile, we actually have 2 greater powers of y in the denominator. Y to the 12th is greater than y to the 10th, so 2 powers of y will remain in the denominator. So the next thing, we're going to go ahead and start looking for those perfect square factors. Additionally, y squared happens to be one of them. So when we go ahead and write it again, like we started, we'll be able to immediately simplify that and ultimately rationalize the denominator as well here. So when we rewrite it, we've got our 16x to the 4th, and then there's also still the square root of x in the numerator. Meanwhile, it's the square root of y squared in the denominator. So if you see what I did here, 16 is a perfect square, 4 times 4, in the same way that x to the 4th power is. X squared times x squared gives us x to the 4th. So that's our perfect square factors that we look for. And I also use my property right here. If I have the square root of something a times b, it's also the same as the square root of a times the square root of b. So that's how I was able to rewrite it in this form. And now we can go ahead and simplify that. In the numerator, we're going to go ahead and have our 4x squared times the square root of x all over y. So I'm going to go ahead and just write it over here. I'll probably erase it when I get to problem 4 and I'll need that space again. So again, this is our final answer, 4x squared, which is, if you were to put that in parentheses, square the whole thing, you would get back to a 16x to the 4th power, and then you multiply it by that leftover x all over y, because we just took the square root of y squared, so those two things canceled out. All right, so the next problem is super easy. All we're trying to do is rationalize the denominator, so we need to get the radical outside of the denominator here. So what we can do first, it's kind of the opposite of what we were doing over here and what we did previously. It already gives us over the whole thing, so we know the square root of 1 is ultimately just going to be 1, but now we're left with the square root of 5 in the denominator. So to rationalize that, we're going to need to multiply the numerator and the denominator by that same square root of 5. So what ends up happening is the square root of 1 just turns into 1. Meanwhile, we still have the square root of 5, and now comes the multiplying here. Square root of 5 times the square root of 5. Well, whatever we do to the numerator, we got to do to the denominator as well. So what we've got here, now in the numerator, we have just the square root of 5. Meanwhile, when you multiply the square root of 5 by the square root of 5, again, the square roots cancel out. That's something we've been doing with our multiplying radicals lesson this week, so hopefully you remember that as well. So the square root of 5 times the square root of 5. So we have successfully rationalized our denominator, and that will be our final answer for that process. Like I said, that one is pretty easy. It's just an important step to remember. We don't want to leave radicals in the denominator. So our last one, I'm going to go ahead and erase part of this problem so it doesn't get in the way. Hopefully you were following along, or you can just rewind to catch it again. So our last step here, we're going to multiply the numerator and the denominator by the conjugate. And what that means is basically going to be the opposite of this. We're still ultimately trying to rationalize the denominator, but since it's a little bit more complicated, it's not just the square root of 5, it's 3 minus the square root of 7. We need to kind of cancel it out and not end up with still having a radical in the denominator. So what we're going to do, we multiply the top by 3 plus the square root of 7, and then we're also multiplying the bottom by 3 plus the square root of 7. All right, so I'm going to go ahead and continue writing this out here. So basically we're just multiplying each of these terms by 5 in the numerator. So now I have my 15, and then plus 5 square roots of 7, and then in the denominator, it's basically just a little bit of that foiling process we've been going over as well. So we need to use that prior knowledge from multiplying radicals in order to continue this next step. I'm going to go ahead, use a black marker to draw some arrows to remind you the process that we're going through. So this 3 obviously needs to multiply by that 3 first, and then we're going to go ahead and multiply it by the square root of 7. So let's take a look at what's going on here with that in the denominator. So now I have 3 times 3 is 9, and then plus 3 square roots of 7. So the next step, we need to go ahead and multiply our negative square root of 7 by the positive 3, and the negative square root of 7 by the positive square root of 7. All right, so this is where it gets interesting. So now you have negative 3 square roots of 7, and guess what? That accomplishes our rationalizing the denominator, because now we can combine those like terms. Ultimately, they'll cancel out, which is why we need to use the conjugate instead of just multiplying it by exactly what it is, where normally that could cancel it out. But for the way this works, we have to use the conjugate, or the opposite sign, basically. So the last step here, we still have the negative square root of 7 times by the positive square root of 7. So when we have the square root of anything multiplied by the square root of that same something, we know it cancels out. The sign will remain, so we're still going to just have that negative 7. So again, we can combine our like terms here. We've got in the numerator our 15 plus 5 square roots of 7 over 9. Our like terms canceled out. That was the goal of using the conjugate, and then it's 9 minus 7. So obviously we can simplify that to just 2. So I'm going to go ahead and write it out again to the side here. So 15 plus 5 square root of 7 all over 2. So that's our last problem. Hope you guys understood the new lesson of dividing radicals. Remember to like, comment, and subscribe.